you, Colin. And so the topic of our presentation today is the applications of NDI and ANSHM technologies in Australian railway industry. So the first author is Ralph Zhang, and Ralph is the PhD student from under our supervision, Helen and myself. And he actually finished the thesis submission, and we got the feedback, very positive feedback, almost done, finished the PhD. But unfortunately, both of them could not be able to join the yesterday and today's workshop. So I'm the representative to present this work. So I'm from the School of Engineering, Design and Built Environment, Western Sydney University, and my office in Paris. And so we have a big research facilities and equipment. Our labs is all over in Paris campus. So we also have our campuses in the Parramatta, so Parramatta Engineering Innovation Hub just opened this year. So we delivered the degree study there. And for research, it's basically in Paris. And for contents wide, so I would like to give a review on the NDI and ANSHM technologies and for the continuous welded rails, and we used it in Australia. And so specifically, and then we gave several case studies. So on the usage of these technologies on the CWR, and also give the concluding remarks. So considering we only have 20 minutes, so I won't give too many information. And I gave the list after I finish my talk for the publications we had, and then you can refer the more details in the publications, so book chapters. Introductions, so you can see the two photos showed below. You can see in the left-hand side, there's a crack. It's basically, that's the continuous weld, the track. You can see CWR, and they have the weld in this part. You can see the weld is here, so it's nearby, but the broken part, the crack is just on top of the sleepers. So you can see the weld part is really strong. The weld itself very strong, but it's happened to have this real broken. And the other photo is showing the buckling. So this happened before in Melbourne, also in the Hunter Valley in Sydney area. So that is also always make big trouble and stop the transportation, and then stop the running, and we have to fix that, repair that. So considering those failures, and we really need to look at how could we prevent those failures and from happening, and then we can have the safe transportation environment for the users or the travelers. And so rail is the most important element of the rail track system. So that is really provide the supporting and the guiding for trains. So that's the why we are focused on this, the very fundamental element. It's so important. And we use the continuous welded rail. So because for that one, we could make the extension as long as possible. So in theory, and we don't want to have any the groove and for separation or gap between the rail tracks. And that's make the train system can travel with a high speed. So high speed train popular in the European country and Asian country, especially in China and Japan. So we don't want to have the gap between the rail tracks. So this is really provided the foundation for the high speed and heavy haul railway system. And so we eliminate the rail joints and the gaps between the rail sections. And but the ambient temperature is always changed during the year. and we could have the negative maybe 10, 15 Celsius and up to 60 Celsius and during the summertime. So the winter and the summer is quite different. So if we're considering in Melbourne is 1 day 4 seasons, and then the ambient temperature is really have a big change. And for example, you could have a 45 degree Celsius in the maybe noon time, and then drop significantly to 16 over midnight. So that's the big change between. And if we considering the change from 60 to down to negative 50, that's a 75 Celsius differences. So that is all generated residual stress problem. So the thermal induced residual stress. So the expansion caused by this temperature change will definitely generate a big problem. So the solution for us, because we want to detect, measure, we want to monitor the situations of the track. So we target at longitudinal thermal stress and look at how this stress, the variation, and how this thermal stress, what's the value are, what's the variation, and then we can considering what's the actions we should take. And if a CWR structure has a poor track maintenance, definitely we don't expect the catastrophic disaster and to happen, and we will have a track buckling and broken rails or derailment. So that is all happening. So in the Australian railway system, and we use the 3 types of the NDI and SH technologies. And for measure this longitudinal thermal temperature, we term as the neutral temperature in-field measurement. So we use a magnetic Barkhausen noise method, and is under the track safe release or real scan different track marks. And we also use the mechanical method, and is under Worth trademark and A-frame method also in another name. And we also use the vibration method, so that's the de-strengthen. So this research really aims to review these 3 NDI and ANSHM technologies and showcase their applications on the neutral temperature in-field measurement. And also we want to identify their advantage and disadvantage for comparison purposes. And first of all, we reviewed what's the NDI and SH technologies for CWRs in our country. And so first one is the magnetic Barkhausen noises technology. And we, in this method, we actually really adopt the magnetic Barkhausen noise MBN method. And in this method, actually, is really look at the field strength and have the relationship with the flow density for the magnetic field. And this is in the left-hand side, you can see the graph is the hysteresis loop. So you can see how this the field strength varied with the flow density. And we use this relationship to set up the neutral temperature and related to the longitudinal stress and also the temperature of the rail. So this is basically what we use. And is a stress dependence of the this magnetic Barkhausen noise. So we basically use this measure to do the collaboration. So, and then we can understand what the temperature is. So it's a link with the noises, link with the stress, and then we get temperature. And so this one also, when you look at this hysteresis loop, and we have different regions, and basically that's region 1, 2, 3. So these different regions, we have different the relationship, and basically we use this principle to measure the neutral temperature. So we could understand what the temperature is, and also we could look at a stress-free condition. So that's the T real, and this one is give the temperature. There's no stress, and the alpha is the basically thermal coefficient of the real, and E is the Young's modulus. So this is we can use the 210 megapascal for the this steel track. So this is the what. So the device it just looks like that, and it's from the track safe release. It's a unit not that big. We can put this device onto the track, and then we can measure the distribution. And in the right hand side, we also have a calibration curve. And for the AIS 107LB, so it's the one of the real track. So it's the basically it's a plain carbon rail, steel rail. So this and we operated this device by means of the non-contact gauging, and it's allowed us to have a faster measurement and documentation of the actual neutral temperature of the rails of our interest. And so this is the first method. So it's non-contact gauging. And the second way is use the so-called Worth or A-free method. So it's a mechanical method and commercialized for measure the neutral temperature. And by using the equipment is the Worth. And the Worth is the technology patented by the Warthog International. And it's based on this beam column bending theory. And in this case, the actual load affects the vertical forces required to lift the rail. So in that case, we lift the rail with the certain kind of height, and then we use the equation to do the calculation. So in such case, you can see we have the force applied to make this one sort of a buckle, and then we measure the force, measure the all these relevant parameters value, and then we use this equation to get this neutral access. So this the principle, and this equipment actually designed and based on the magnetoelastic principle to measure the stress distribution and the neutral temperature of a continuous this welded rail. And we also give some photos, and you can see this equipment installed on the track. So this is definitely the contact measurement. And we measure this temperature, neutral temperature, which very high accuracy. So it's 0.2 Celsius, and also a standard deviation is 1.3 Celsius. So this
2 minutes,
method,
Richard. Thank you.
Okay. All right. So I need to fast. Yeah, thank you, Colin. So the method can be used for different kinds of the rails and get instant results, and by using the equation. And the last one is the vibration method. So this strengthened. So this method have potential to estimating the TN condition quickly and non-destructively. So it doesn't like the mechanical method. System components, including the variable speed shaker and the 2 bar and with accelerometer, magnetic real temperature probe, and the data acquisition system. You can see what's the setting. So pretty much it's just activated the vibration, and then we do the measurement. And because of the time, so I just gave some showcase quickly. So the first one is ambient technology. So you can see the in-track measurement and perform using this real scan neutral temperature measurement device. And this one is in the North Coast line in the Gloucester in New South Wales. And it's working on 8 working days to do the measurement. And we have the results here. So from the calculation, so the purple one is a calculated method that gets the results, and the blue one is what we measured. So you can see, and when the frequency number of the CWS modules lower, they are very close. And if it's higher, it's becoming have a bit larger discrepancy and a different trend. So this is what we cut this reel and the location to do the measurement. And also compared to the mechanical method, and this mechanical method, you can see we use the railway scan and the real scan versus, and also temperature difference for measurement. And you can see these two methods very well, have a good agreement. And just as in the photo, left-hand side, that is the basically what Ralph, so Ralph is doing the reading. And the vibration method, we do the de-strengthen. So this one have potential that's splitting the neutral temperature condition quickly and non-destructively as well. And this one is really operate open speed, overall speed range, 65 to 80 Hertz. And after installation, we can have the computer control the motor and doing the narrow sweep encompassing the cantilever for band resonance and record the largest resulting the peak-to-peak velocity signal. So according to this, the signal, we can do the processing, and then we collect the data to determine what's the results looks like. So comparison between these three, and we could say they have a different the advantage and disadvantage. So for both the first two methods, we don't need to do the track work, but for the worst mechanical method, we have to lift up the track. So, and the first two methods, there's no limitation, but for worst, the mechanical one, definitely we need to be careful when the radius, the curvature is too big. So it's not for the ballast bridge or location close to the fixed points. And the others also have the temperature issue for the worst mechanical method. So to us, we can draw the conclusion that, and these three methods can be used and also are being used. And this strengthen method is most flexible and efficient one with the least limitation among all three technologies. And the worst method, the mechanical method, provides the highest precision, but it takes more time and labors to finish the on-site measurement. And the magnetic Barkhausen noises method sit in the middle, which is the advantage and limitations. And for detailed information, please refer to our chapter, and that's edited by Tommy and Hong, and also Gentrin. So it's just 2022. We also have another chapters so published in the spring by the Springer. All right, so thank you so much. If you have any questions, please let me know. And if you want to have a further contact, that's my information for contact details. Thank you so much, Colin. Sorry for the time.
No, it's okay. We thank you, Richard. Thank you.
Always.
So we have time just for maybe one question, if anyone has one. Yep.
Okay.
Hi, Richard. Thank you for your presentation. Very interesting. My question is, I noted that when you took all the measurements, it was during the day. And my experience of monitoring rail, on either side of the rail, you can have differences in the strain profiles due to the temperature gradient, depending on where the sun is. Was that, and did that affect your measurements at all? Did you need to do it when the sun was immediately above you, or was there an advantage to doing it at night? I'd love to hear your thoughts on that.
Yeah, thank you so much for this very practical question. And I wish Ralph could be here. He's the site engineer. So actually, I remember when we had a discussion, they are not picking up what's as data or night to do the work. It's really up to, they have a routine. I remember it's routine maintenance. They could do it in the early morning. It's very early morning. I don't remember they do any night work, but the early morning, we say 3 or 4 at 3 or 4 o'clock. So they do that work. I remember like that. So it's peaky, not definitely not in the midday, and considering the sunlight. Yeah. So that's so far as I know. Yeah.
Thank you so much, Richard, and great presentation on complex but important work. Well done.
Thank you very much, Colin. Thank you, everyone. Yeah, have finished. I just stopped.